Hybrid RAG gets messy when keyword search, vectors, and reranking live in separate places. Vespa lets you serve them as one search engine. After this, you'll understand how to assemble a pipeline that blends search signals, picks context, and drafts an answer. I'm Professor Pi, teaching AI engineering and LLM systems with simple Python. Vespa Hybrid Search in Python solves a common pain in retrieval augmented generation. Teams often end up wiring a keyword index, a vector store, and a reranker together, then spending days debugging ID handoffs. What we want instead is a single maintainable search endpoint that returns solid context for a model without extra RPCs. Vespa helps because it can store lexical indexes, vector fields, and ranking logic inside one serving layer, so you avoid duplicated ingestion and cross-service joins. Hybrid search is simply the mix of exact term signals and semantic signals. Picture a user who quotes an error message, but also asks a broad configuration question. Sparse search finds the exact error text. Dense vectors surface semantically related troubleshooting steps. A fusion rank then weighs both and picks the best passages. In practice, that gives a model richer context at modest extra latency. We will build a tiny RAG baseline in Python that shows readiness checks, feeding documents, a BM25 lookup, a vector lookup, and a fused rerank. That keeps the example compact and directly tied to real retrieval behavior. Quick note: this code is designed to teach the core idea clearly. Library versions and local setups can vary, so check the official docs if your setup behaves differently. First, we verify our Python client can reach a local Vespa instance and serve queries. This snippet performs a lightweight readiness check to show whether a local Vespa endpoint responds. The pyvespa object points at localhost 8080, and app.syncio connections equals 1 opens a small synchronous client session for one cheap query. The YQL asks Vespa for 0 hits, so it's not doing real retrieval, just confirming the serving layer answers requests. The visible output tells you whether session.query succeeded, which matters because every later BM25, vector, and reranking call depends on this same app. With connectivity verified, we need content indexed in the same app, so lexical and vector features align. I will feed a tiny readable corpus into Vespa, so both stores share the same documents. This example feeds a small, inspectable RAG corpus into Vespa, so the same documents back both lexical and vector fields. Separate keyword stores and vector stores can drift when ingestion paths are duplicated. Here, raw docs stays easy to inspect on screen, and docs converts each tuple into the ID and field shape pyvespa expects. The call names the doc schema and RAG namespace, so Vespa knows where to index these records. The visible output reports how many documents were sent, which is important because retrieval quality only matters once content is indexed. Now we want a lexical baseline so we know what exact term matching returns. Running a BM25 search gives a simple, interpretable baseline before we add vectors. This code runs the sparse retrieval side, so we see what exact term matching returns. Keyword search still pays off when users include product names, stack traces, or error messages that embeddings can blur. The YQL uses user query to bind the Python query string into Vespa matching, and ranking equals BM25 picks the lexical rank profile. The top hit comes back from BM25.hits, including Vespa's relevance value for that ranking path. The visible output shows the best lexical document and its score, giving us a concrete baseline to compare against later. Lexical hits are fine, but we also want semantic matches for paraphrases and concept-level similarity. Next, we switch to vector search within the same Vespa session, so the two paths share features. This example runs semantic matching inside Vespa, so you get paraphrase and concept-level candidates. In many RAG systems, a separate vector DB gets bolted on, but here, nearestNeighbor embedding Q runs inside the same session query call. The body passes input, query Q as embed query, letting the configured Vespa embedder produce the query tensor the semantic rank expects. Target hits 10. Controls how many vector candidates Vespa considers before applying the final limit. Raise it for better recall, lower it to save work. The output shows the top semantic match and score, which complements the BM25 baseline. Now, we combine both sparse and dense signals and let Vespa re-rank candidates using both kinds of evidence. We run a fusion ranking profile so Vespa compares lexical and semantic features together. This snippet merges the retrieval paths, so Vespa re-ranks candidates using both dense and sparse evidence. The rank operator retrieves nearestNeighbor embedding Q candidates, while also evaluating user query, letting the fusion rank profile weigh both signals. That keeps candidate generation, feature calculation, and re-ranking inside Vespa, instead of passing IDs between services. The Python change is minimal. A new YQL, ranking equals fusion, and the embedded query input define the hybrid behavior. Increasing target hits 20 gives the re-ranker more candidates to compare at the cost of extra latency. The output shows the final re-ranked document and score, completing a compact hybrid RAG retrieval baseline. In a real project, this maps to a help center or knowledge base. Replace the tiny corpus with your actual FAQ entries, error logs, or product docs, and keep the same pattern: one ingest path, one serving app, and a single endpoint that returns fused candidates for the model. The short takeaway: you can serve lexical hits, vector hits, and a fused re-rank from one Vespa endpoint. Use this pattern when you need both exact term matching and semantic recall, but don't want to juggle multiple services. One caveat: more candidates for re-rank improves recall, but it also raises latency. So measure the trade-off on your queries. Try one focus change next. Tune target hits from its baseline of 20 to see how recall and latency shift, and simultaneously adjust BM25 K1 and B in your rank profile to balance lexical weight. Measure re-rank precision on your own corpus and use that to pick a working point. If short, practical AI engineering helps, subscribe and watch the AI engineering videos.